26,000 light-years from Earth, behind so much dust that ordinary light can barely escape. The center of our galaxy is doing something we still cannot fully explain. There is a black hole there, not a small one, not a dying star. A monster 4 million times heavier than our sun. But the black hole is only the beginning. Around it, stars whip through space at speeds so extreme that Einstein's theory of gravity can be tested in real time. Objects that look like clouds pass close enough to be ripped apart, yet somehow come out the other side still alive. An invisible barrier appears to block some of the fastest particles in the universe from entering the galactic core. And surrounding the entire region is a strange glow of gamma rays that may come from dead stars, or from something far stranger, dark matter destroying itself in the heart of the Milky Way. For centuries, the Milky Way looked peaceful from Earth, a pale river across the night sky. A soft band of light made of countless distant stars. But that calm appearance was an illusion, because at the center of that river, hidden behind dust, radio noise, magnetic fields, dead stars, and extreme gravity, there is a place where almost every model starts to bend. Tonight, we travel into that place, past the dusty arms of the galaxy, past the region where visible light disappears, past stars moving faster than anything their size should ever move. Into the dark engine, our entire galaxy orbits. And the deeper we go, the more one thing becomes clear. The center of the Milky Way is not quiet. It is not simple. And it may be hiding one of the most important clues in modern physics. Prepare yourselves. We begin. The first time humanity found the center of the Milky Way, we did not see it. We heard it. Not as music, not as a signal anyone could understand, but as static. In the early 1930s, an engineer named Karl Jansky was working for Bell Telephone Laboratories in New Jersey. His assignment had nothing to do with black holes, dark matter, or the structure of the galaxy. He was trying to solve a practical problem. Something was interfering with transatlantic radio phone calls. There was a hiss in the signal, a crackle, a background noise that would not go away. Most people expected the source to be ordinary. Thunderstorms, electrical equipment, atmospheric disturbances, something on Earth. So Jansky built a strange machine in a field. It was a rotating radio antenna, mounted on wheels made of wood, wire, and metal pipe. It looked less like an observatory and more like a broken amusement park ride. People called it Jansky's merry-go-round. Day after day, it slowly turned, listening to the sky. At first, the results were exactly what he expected. Some noise came from nearby storms, some came from distant storms, some came from the ordinary electrical mess of the modern world. But one signal refused to behave. It returned again and again, not on the schedule of the sun, on the schedule of the stars. That detail changed everything. If the noise came back with the stars, then it was not coming from weather. It was not coming from New Jersey. It was not coming from Earth at all. It was coming from space. After months of tracking it, Jansky realized the strongest radio noise was coming from the direction of Sagittarius, the direction of the center of the Milky Way. Imagine that moment. A man standing in a field trying to fix phone calls accidentally discovers that the heart of the galaxy is broadcasting. The center of the Milky Way was screaming in radio waves, and nobody had known how to listen. At the time, astronomy was still mostly a science of visible light. Telescopes collected what the human eye could never gather on its own, but they were still extensions of sight. Radio astronomy barely existed. The idea that the universe could be loud in wavelengths human beings cannot see felt almost absurd. Jansky published his discovery, Then the world mostly moved on. For a while, one of the most important signals in astronomy sat there, noticed but not fully understood. Years later, an amateur scientist named Grote Reber built a radio dish in his own backyard in Illinois. He was not commanding a giant observatory. He was not running a national space program. He simply became obsessed with what Jansky had found. So he built a dish. He pointed it at the sky, and he confirmed the impossible. The Milky Way was glowing in radio waves. The strongest emission came from its center. Something was there, something powerful, something hidden. And the strangest part was that when astronomers looked at that region with ordinary optical telescopes, they did not see anything that matched the power of the signal. There was no obvious giant object shining in visible light, no blazing central star, no bright lighthouse marking the core, just dust, darkness, obscured starlight. The center of the Milky Way was speaking clearly in radio waves and hiding completely in visible light. That contradiction became the beginning of a century-long mystery, because between Earth and the galactic center lies one of the greatest obstacles in observational astronomy. A wall of dust. Not dust like the dust on a shelf. Cosmic dust. Tiny grains of carbon, silicates, ice, and heavy elements scattered through the spiral arms of the galaxy. Individually, they are microscopic. Across 26,000 light-years, they become a curtain. Visible light from the galactic center cannot pass through cleanly. It gets absorbed, scattered, blocked. To human eyes, the heart of our galaxy is almost invisible. That is the first strange truth about the Milky Way. We live inside it, but that does not make it easy to understand. It makes it harder. Trying to map the galaxy from Earth is like standing in the middle of a crowded forest at night and trying to draw the shape of the entire forest from the shadows between the trees. You can see what is nearby, you can infer what is far away, but the full structure has to be reconstructed piece by piece. For decades, astronomers built better instruments to do exactly that. Radio telescopes listened through the dust. Infrared telescopes saw heat where visible light failed. X-ray telescopes watched violent flares. Gamma-ray telescopes mapped the most energetic processes in the region. And slowly, the hidden center began to sharpen. The radio source near the middle of the galaxy became known as Sagittarius A. Inside that region was an even more compact source, Sagittarius A star. A tiny-looking point in the data with a massive secret. For a long time, astronomers suspected what it might be. A supermassive black hole, the kind of object so dense that nothing, not even light, can escape once it crosses the event horizon. But suspecting a black hole and proving one are very different things. A black hole does not glow like a star. You cannot simply point a telescope at it and see its surface. It has no surface. It has a boundary, a point of no return. To prove that one exists, you have to watch what it does to the space around it. You have to look for the invisible hand by watching everything it pulls. So astronomers started watching the stars, not the stars around Earth, the stars near the galactic center. Infrared telescopes could cut through the dust enough to track them. Night after night, year after year, two major teams followed tiny points of light near Sagittarius A star. At first, their movement looked almost impossible. These stars were not drifting gently. They were racing, curving, looping, swinging around something that could not be seen. One star became the key, S2, a star close enough to the galactic center and moving fast enough that its orbit could be measured within a human lifetime. S2 completes one orbit in about 16 years. For comparison, our Sun takes roughly 230 million years to make one orbit around the Milky Way. S2 does its lap in less time than it takes a child to grow up. At its closest approach, S2 flies past Sagittarius A at several percent of the speed of light. Not a spacecraft, not a particle, an entire star, moving through space at millions of miles per hour. The motion told the truth. Something with about 4 million times the mass of the Sun was sitting at the focus of S2's orbit, and that mass had to be packed into a region so small that no cluster of ordinary stars could explain it. A dense star cluster would shine. A cluster of dead remnants would not stay stable for long. The cleanest explanation was also the most extreme. A supermassive black hole. Two teams working independently for decades reached the same conclusion. Their measurements turned the invisible object from theory into reality. A black hole sits at the center of the Milky Way. Sagittarius A, 4 million solar masses, the dark anchor of our galaxy. But once scientists proved the black hole was there, the mystery did not end. It multiplied. Because the region around Sagittarius A is not behaving like a simple system. It is crowded with young stars that should be difficult to form there. It contains objects that look like gas, but survive like stars. It flickers in ways that are still being studied, and it sits inside a larger environment filled with magnetic fields, high-energy particles, strange radiation, and dense molecular gas. The black hole was not the final answer. It was the doorway. The first major problem is the stars. The region near a supermassive black hole should be a terrible place to make young stars. Stars normally form inside cold clouds of gas and dust. The cloud has to collapse under its own gravity. It has to cool. It has to fragment into dense knots. Slowly, those knots become stars. But the galactic center is not calm. Gravity changes violently over short distances. Radiation is intense. Gas is heated and stirred. The black hole's tidal forces can tear weak structures apart before they ever settle. It is not the kind of nursery where young stars should easily appear. And yet, they are there. Hot, massive, young stars orbit near the black hole. This is known as the paradox of youth. The name sounds almost poetic, but the problem is real. Some of these stars look too young to have traveled there from far away, but the environment looks too violent for them to have formed there normally. One idea is that they formed farther out in a dense cluster, and that cluster slowly migrated inward before being torn apart. Another idea is that a dense disk of gas once surrounded the black hole and fragmented into stars under extreme conditions. Both explanations are possible. Neither makes the center simple. The stars are a reminder that Sagittarius A is not sitting in empty space. It lives inside a chaotic ecosystem, a place where gravity can destroy, but may also force matter into strange new forms. And the strangest forms of all may be the G objects. They are some of the most unsettling things astronomers have found near the center of the Milky Way, because they refuse to fit neatly into one category. They move like stars, but they look like gas clouds. That sentence should not be normal. A star is compact. A gas cloud is diffuse. A star can survive close gravitational encounters. A loose gas cloud should be stretched, shredded, and smeared out by the tidal forces near a black hole. The G objects seem to live in between. One of them, called G2, became famous because scientists thought they were about to watch it get destroyed. G2 was on a path that would bring it close to Sagittarius A star. If it were just a cloud of gas, the prediction was dramatic. The black hole would stretch it. The front of the cloud would be pulled harder than the back. The object would elongate into a stream. Some of that material might fall inward. Sagittarius A might flare as it consumed fresh gas. For astronomers, This was a rare opportunity, a possible feeding event at the closest supermassive black hole to Earth. Telescopes watched, models were built. The date of closest approach came. And for a while, the prediction looked right. G2 stretched, it elongated, its shape changed under the black hole's gravity. Then the impossible part happened. It survived. The huge flare did not arrive. The object did not dissolve into a simple stream of debris. It passed around the black hole and continued on its orbit, changed, but still recognizable. That is not how an ordinary gas cloud should behave. Once a cloud like that gets pulled apart, it does not politely gather itself back together. Something inside G2 had to be holding it together. The leading explanation is that G objects are not pure gas clouds at all. They may be merged binary stars. Imagine two stars orbiting each other too closely in the crowded, gravitationally violent environment near the galactic center. Over time, interactions with the black hole and nearby stars can tighten their orbit. The two stars spiral closer. They collide. They merge. The result is a swollen stellar object wrapped in a thick envelope of dust and gas. From the outside, it looks fuzzy, like a cloud, but hidden inside is a real star-like core. That core gives the object enough structure to survive when the black hole tries to tear it apart. Picture a stone wrapped in smoke. From far away, you see the smoke. When wind hits, the smoke twists and stretches, but the stone keeps moving. That may be what G2 did. It was not a cloud surviving the impossible. It was something disguised as a cloud. But the disguise still matters, because it tells us the galactic center can create objects we would not expect elsewhere. Star mergers wrapped in debris, cloud-like bodies with hidden cores, things born from violence then forced to orbit the most extreme object in the galaxy. And even now, we cannot easily see inside them. The dust is too thick, the objects are too far. The region is too crowded, so they remain partly mysterious. 6 strange bodies, moving like stars, looking like gas, surviving where survival should not be easy. For decades, Sagittarius A star itself remained invisible except through its effects. We watched stars orbit it. We measured radio waves from it. We caught flares from the region around it. But we did not have an image of the black hole's shadow. Then came the Event Horizon Telescope. The Event Horizon Telescope is not a single telescope. It is a planet-sized collaboration. Radio observatories across Earth observe the same target at the same time, and their data is combined so precisely that the entire Earth behaves like one enormous telescope. That is the kind of instrument required to see something as small and distant as a black hole shadow at the center of the Milky Way. In 2019, the Event Horizon Telescope released the first image of a black hole, the giant black hole in the galaxy M87. That object is billions of times the mass of the Sun. Huge, slow-changing, comparatively easier to image. Sagittarius A star was different. It is much smaller. Not small in any human sense, but smaller than M87's black hole. The gas around it moves quickly, changing on timescales of minutes. Trying to image it was like trying to photograph a spinning spark with a camera that needs hours of exposure. The object changes while you are still collecting the light. For years, scientists worked through the data. Then, in 2022, the image was released. A glowing ring, a dark center. Orange radio light bent around a shadow. It looked similar to the M87 black hole image, but this one was ours, the black hole at the heart of the Milky Way. The ring was not the event horizon itself. Nothing inside the event horizon sends light back to us. The ring was hot material near the black hole, shaped by extreme gravity. The darkness in the middle was the shadow, the region where light is swallowed or bent away. The size matched predictions for a black hole of about 4 million solar masses. It was one of the strongest confirmations yet that Sagittarius A star is exactly what the stellar orbits had implied: a supermassive black hole. But again, the confirmation did not make the region simple, because Sagittarius A star is weirdly quiet. Compared with the central black holes of active galaxies, ours is underfed. It is not blazing as a quasar. It is not launching a powerful jet bright enough to dominate the galaxy. Most of the time, it sits in a low state. Then suddenly, it flares. Infrared and X-ray brightness can jump, then fade. The cause of these flares is still studied. Maybe small clumps of gas fall inward. Maybe magnetic fields twist and reconnect, releasing stored energy in bursts. Maybe hotspots form in the accretion flow and orbit briefly before disappearing. The image gave us the face of the monster, but not all of its habits. And beyond the black hole itself lies an even larger mystery. A boundary around the central region. A barrier that seems to stop some of the fastest particles in the universe. Cosmic rays sound like beams of light, but most of them are actual particles. Protons, atomic nuclei, sometimes electrons. They move through space at nearly the speed of light. They are produced by supernova explosions, pulsars, black hole environments, and other violent astrophysical events. They cross the galaxy constantly. Right now, cosmic rays are striking Earth's atmosphere above you. Most never reach the ground because the atmosphere absorbs them, but in space, they are a serious hazard. For astronauts outside Earth's magnetic protection, cosmic rays are one of the invisible dangers of deep space. They are extremely hard to stop, which is why the center of the Milky Way surprised scientists. The central molecular zone is a dense region of gas and dust surrounding the galactic core. It should be exposed to cosmic rays from the wider galaxy. These particles should stream in from outside, mixing with the environment inside. But observations suggest something strange. The cosmic ray density inside the central molecular zone appears lower than expected, as if incoming cosmic rays reach the edge of the region and are blocked, deflected, or pushed away. An invisible wall, not a wall made of matter, a wall made of fields, plasma, and motion. That sounds dramatic, but the physics is real. Cosmic rays are charged particles, and charged particles respond to magnetic fields. A strong enough magnetic structure can bend their paths. It can redirect them. It can make a region harder to enter. The galactic center has unusually strong and tangled magnetic fields. Stars are densely packed. Gas is ionized. Supernovae inject energy. The black hole's environment stirs plasma. All of that can amplify magnetic structures. One explanation is that magnetic fields near the edge of the central molecular zone form a kind of shield, guiding incoming cosmic rays around the region instead of letting them pass straight through. Picture rain hitting a slanted roof. The water does not disappear. It is redirected. Another explanation is wind. The galactic center may drive hot gas outward through supernovae, massive star winds, and activity near Sagittarius A star. If particles created inside the region are carried outward by this flow, they can escape. But particles trying to enter from outside must fight against the current. In that case, the central molecular zone behaves almost like a one-way membrane. Things can get out more easily than they can get in. The real answer may be both. Magnetic fields and galactic winds working together. A shield and a current. A barrier written not in stone but in charged particles and invisible lines of force. Why does this matter? Because cosmic rays are not just fast. They change chemistry. When they enter gas clouds, they ionize molecules. They trigger reactions. They affect how gas cools, how it collapses, and how stars form. If the central molecular zone is partly shielded, then the chemistry inside the galactic center is different from the chemistry outside it. The core of our galaxy becomes a separate chemical world, a laboratory sealed by magnetic fields and wind. And inside that laboratory is another unsolved signal, a glow of gamma rays. Gamma rays are the most energetic form of light. They come from extreme events: nuclear reactions, particle collisions, supernova remnants, pulsars, and the regions around compact objects. When NASA's Fermi Gamma Ray Space Telescope mapped the sky, it found something unusual near the galactic center: an excess. More gamma rays than the simplest models predicted. The glow was centered around the core. It had a particular energy range. It extended outward in a way that caught attention immediately, because one possible explanation had been predicted long before the signal became famous. Dark matter. Dark matter is one of the deepest problems in physics. We know it exists because of gravity. Galaxies rotate too quickly for the visible matter they contain. Galaxy clusters hold together with more gravity than ordinary matter can provide. Light from distant objects bends around invisible mass. The large-scale structure of the universe only makes sense if most matter is not made of atoms. But we do not know what dark matter is. We know its gravitational fingerprints. We do not know the particle. One candidate is a weakly interacting massive particle, often called a WIMP. If WIMPs exist, they may sometimes collide and annihilate, converting their mass into other particles, including gamma rays. The center of a galaxy should be one of the best places to look, because dark matter should be densest there. So when a gamma ray excess appeared around the center of the Milky Way, scientists paid attention. The energy range looked interesting. The location made sense. The shape was close enough to certain predictions to make people wonder. Could this be the first indirect signal of dark matter particles? If yes, it would be one of the greatest discoveries in the history of science. Not just evidence that dark matter has gravity, evidence of what dark matter actually does. But there is another explanation, and it is almost as fascinating: millisecond pulsars. A pulsar is a dead star's core. When a massive star explodes as a supernova, its core can collapse into a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. Some neutron stars spin rapidly and sweep beams of radiation through space. If the beam points toward Earth, we see pulses. Millisecond pulsars spin hundreds of times per second. They are ancient, stable, fast, and they emit gamma rays. The galactic center may contain a huge hidden population of them. Individually, they may be too faint to resolve. Together, they could create a glow that looks smooth. A city of dead stars, each too dim to see alone, merging into one diffuse light. That is the problem. Dark matter annihilation and a hidden population of millisecond pulsars can look frustratingly similar. Same region, similar energy, similar glow. Scientists call this kind of problem a degeneracy. Two different causes produce the same observed effect. The data cannot easily choose. Some analyses suggest the gamma ray excess is smooth, which would support dark matter. Other analyses suggest it has the statistical texture of many faint point sources, which would support pulsars. Both sides have arguments. Both sides have models. And the galactic center is so messy that background subtraction becomes incredibly difficult. Gas clouds overlap. Cosmic rays interact with matter. Known gamma ray sources crowd the field. Large structures like the Fermi bubbles complicate the sky. Change the background model, and the excess can change with it. This is why no one can honestly say dark matter has been discovered there. It has not. But no one can honestly say the mystery is boring either, because both major answers are extraordinary. If the glow is pulsars, then the center of the Milky Way hides an enormous unresolved population of spinning, dead stars. If the glow is dark matter, then we may be seeing the invisible matter of the universe finally revealing itself through light. Either way, the center is telling us something. We just do not yet know which language it is speaking. And while gamma rays glow from the region, radio telescopes have found another kind of signal, something that turns on and off, something compact, something highly polarized, something that does not fit neatly into the usual categories. In 2021, astronomers reported a strange radio transient toward the galactic center. Its formal name is long and difficult to remember. ASCAP J 173608.2 -3-2-1635. Some people informally called it Andy's object. The name matters less than the behavior. It appeared in radio waves, then faded, then came back. Its signal was highly polarized, meaning the radio waves were organized in a way that usually points to a strong magnetic field. But the source did not behave like an ordinary pulsar. Pulsars tick. They have periods. Some are so stable that they rival atomic clocks over long timescales. This object was not so simple. It did not fit cleanly as a standard flare star. It did not match an ordinary magnetar outburst in an obvious way. It seemed to belong to a growing family of strange radio transients that modern surveys are only now beginning to uncover. This happens again and again in astronomy. The universe does not suddenly invent new objects when we build better instruments. The objects were already there. We simply could not see them before. Before radio astronomy, the galactic center was silent to us. Before infrared astronomy, its stars were hidden. Before gamma-ray telescopes, the excess was invisible. Before modern transient surveys, strange radio sources could switch on and off between observations without anyone noticing. Now, the sky is being watched more carefully. And the weird things are starting to appear. Highly polarized radio waves are not just interesting because they are unusual. They are clues. As radio waves travel through magnetized plasma, their polarization can rotate. This effect is called Faraday rotation. By measuring it, astronomers can learn about magnetic fields and electron density along the path the light traveled. Toward the galactic center, these measurements can be extreme. That tells us the magnetic environment is powerful and complicated. And magnetism may be one of the hidden keys to the entire region. It may help shape the cosmic ray barrier. It may help trigger flares near Sagittarius A star. It may control how particles move through the central molecular zone. It may influence strange radio transients. In everyday life, magnetism feels simple. A magnet sticks to metal. A compass points north. At the center of the galaxy, magnetic fields are invisible architecture. They guide plasma. They store energy. They bend particle paths. They may decide what enters the core and what escapes it. And we are still mapping them. That is one reason the galactic center is so difficult to understand. The mysteries overlap. The black hole affects gas. Gas affects star formation. Stars become supernovae. Supernovae accelerate cosmic rays. Cosmic rays change chemistry. Magnetic fields steer cosmic rays. Dead stars mimic dark matter. Dark matter may affect orbits. Everything touches everything else. Pull one thread and the whole center moves. That is why simple explanations keep failing. The central molecular zone itself is a perfect example. This is the dense reservoir of molecular gas surrounding the Milky Way's core. It spans hundreds of light years and contains tens of millions of solar masses of gas. That is enough raw material to form enormous numbers of stars. So you might expect the region to be a furious star factory. Dense gas should collapse. Collapsed gas should form stars. But the central molecular zone forms stars less efficiently than simple models predict. The gas is there. The mass is there, the pressure is high, but something holds much of it back. Turbulence may keep the clouds stirred. Magnetic fields may support them against collapse. Tidal forces may stretch and shear them. Feedback from young stars and supernovae may heat the gas. The answer is probably not one thing. It is the entire environment. The central molecular zone is not a calm nursery. It is a storm. A dense, hot, magnetized, turbulent storm orbiting the darkest object in the galaxy. Inside it, chemistry becomes unusual. Molecules form under conditions very different from the quieter clouds closer to our solar neighborhood. Gas temperatures are higher. Shocks are common. Radiation fields are stronger. The result is a region that behaves almost like its own world. A sealed, violent chemical engine at the center of the Milky Way. Now step back and look at the whole picture. At the very center, Sagittarius A star. 4 million solar masses. A black hole we have finally imaged, but still do not fully understand. Around it, stars move so fast that their light shifts under gravity. Some of those stars are young enough to create a paradox. Near them, G objects survive close passages that should destroy simple gas clouds. Around the region, cosmic rays appear to meet an invisible barrier. Across the core, gamma rays glow with an origin still debated. Inside the radio data, strange transients flicker in and out. Through all of it, magnetic fields twist like invisible bones. This is not a peaceful galactic center. It is an engine room, a place where gravity, radiation, magnetism, particle physics, star formation, and dark matter all collide. And the most unsettling part is that this is not some distant alien galaxy. This is home. The Milky Way is our galaxy. Sagittarius A star is our central black hole. Our sun orbits it with the rest of the galactic disk. One orbit takes roughly 230 million years. The last time our solar system was near this same point in its galactic year, dinosaurs were beginning to dominate Earth. Since then, continents have shifted, species have appeared and vanished, oceans have opened and closed. But the galactic center has remained there, hidden in Sagittarius, pulling the entire disk around it. We do not feel it in daily life. The scale is too large, the motion is too smooth, but every star in the Milky Way is part of that larger dance, including us. That is what makes the center so fascinating. It is both unimaginably far and deeply connected to us. A place 26,000 light-years away that still defines the structure of our cosmic home. A monster we cannot visit, but cannot ignore. And it may not always have been as quiet as it is now. Today, Sagittarius A star is underfed compared with the black holes in active galaxies. But giant structures above and below the Milky Way, known as the Fermi bubbles, suggest the central region has released enormous energy in the past. Maybe from black hole activity. Maybe from bursts of star formation and supernovae. Maybe from both. The Milky Way may seem calm in human time, but galaxies live on different clocks. A quiet black hole can become active if fuel reaches it. A molecular cloud can change the feeding rate. A star can pass too close. A flare can erupt. The center is not dead. It is slow, and slow is not the same as safe or simple. Human beings are not built to intuit million-year processes. We see a calm night sky and imagine permanence. But galaxies evolve. Black holes feed. Stars die. Gas falls inward. Magnetic fields twist and reconnect. Particles accelerate to nearly light speed. The Milky Way is alive in the only way a galaxy can be alive. Not biologically, dynamically, changing, cycling, reacting, reshaping itself across deep time. And at its center, the most extreme clues are still waiting. Future telescopes will change this story. The next generation of Event Horizon Telescope observations may show how hot gas moves around Sagittarius A star, not just what the average shadow looks like. More infrared monitoring may reveal new stars, new G objects, and more precise orbits. Better gamma-ray instruments may finally separate dark, matter-like diffuse emission from unresolved pulsars. Powerful radio arrays may map the magnetic field and find more strange transients. Each new instrument gives humanity another sense. Visible light gave us the stars. Radio gave us the hidden center. Infrared gave us the orbits. X-rays gave us flares. Gamma rays gave us the high-energy glow. Polarization gives us magnetic structure. Together, they turn the invisible into something we can study. Not completely, not perfectly, but enough to know that the center of the Milky Way is far stranger than it looks from a dark field on Earth. And maybe that is the real lesson. The universe does not become less mysterious when science improves. It becomes mysterious in sharper detail. Before Jansky, the galactic center was just a hidden direction in the sky. After radio astronomy, it became a source. After infrared astronomy, it became a system of racing stars. After decades of orbital tracking, it became a confirmed black hole. After the Event Horizon Telescope, it became an image. After Fermi, it became a gamma-ray puzzle. After cosmic ray studies, it became a region with an invisible boundary. After modern radio surveys, it became a place of strange transients. Every answer opened a deeper room. That is what real mystery looks like, not a lack of facts. A growing pile of facts that do not yet fit into one simple picture. So when someone says something impossible is happening at the center of the Milky Way, the word impossible does not mean magic. It means something more interesting. It means impossible for our first assumptions. Impossible for the simple version. Impossible until the next model is built. The G objects are not impossible if they hide merged stars. The gamma-ray glow is not impossible if it comes from pulsars. The cosmic ray wall is not impossible if magnetic fields and winds shape it. The young stars are not impossible if they formed in a disk or migrated inward. But each explanation requires the galactic center to be more complex than we wanted it to be. And that is usually how the universe wins. Not by breaking physics, by using physics in combinations we did not expect. Right now, Sagittarius A star is still there. 4 million suns worth of mass, hidden inside darkness. Stars continue to orbit it. Gas continues to move around it. Magnetic fields continue to twist. Cosmic rays continue to scatter. Gamma rays continue to glow. Radio sources continue to flicker. And 26,000 light-years away, on a small planet in the same galaxy, we keep building better ways to listen. The next signal may already be traveling toward us. Maybe it left the galactic center before the first human cities existed. Maybe it left before agriculture. Maybe it left before our species learned to write down the sky. It is crossing the dust now, threading through the galaxy, heading for instruments we may not have built yet. And when it arrives, the story may change again. Maybe the gamma-ray glow will resolve into thousands of dead stars. Maybe it will become the first real sign of dark matter interacting with itself. Maybe more G objects will reveal a hidden history of stellar mergers near the black hole. Maybe the cosmic ray barrier will turn out to be part of a larger galactic circulation system. Maybe the strange radio transients will become a new class of object. Or maybe the center of the Milky Way will do what it has always done. give us an answer that creates 3 better questions. Until then, the secret remains. Hidden behind dust, wrapped in magnetic fields, lit by gamma rays, surrounded by impossible stars, anchored by a black hole we can finally image, but still cannot fully understand. The center of our galaxy is not silent. It never was. We just had to learn how to hear it. And now that we can, the sound coming from the heart of the Milky Way is telling us something unsettling. Something is happening there, something powerful, something ancient, something we are only beginning to understand. Before we move into the radio signals, we need to pause on the gamma ray mystery a little longer, because the glow itself is not the only strange thing Fermi revealed. Above and below the center of the Milky Way, stretching out of the galactic disk like 2 enormous invisible lungs, are structures so large that they make the central black hole feel small. They are called the Fermi bubbles, and they may be scars. Each bubble extends tens of thousands of light years away from the galactic plane. One rises above the disk, one drops below it. Together, they form a giant hourglass of high-energy radiation, centered almost perfectly on the galactic core. If human eyes could see gamma rays, the night sky would not look calm. The center of the Milky Way would appear to have 2 vast glowing lobes erupting from it, like the aftermath of some ancient explosion. The strange part is that nobody knows exactly what created them. One explanation is that Sagittarius A star was much more active in the past. Maybe not today, maybe not during human history, but sometime in the last few million years, enough gas may have fallen toward the black hole to wake it up. Not into a full quasar. Not into the kind of monster that outshines its entire galaxy, but into something powerful enough to launch energy far above and below the Milky Way's disk. Another explanation is star formation. The central region of the galaxy contains massive stars, supernova remnants, and violent stellar winds. If enough massive stars formed and died in a concentrated burst, their explosions could have driven hot plasma outward, inflating the bubbles from below like pressure building inside a sealed chamber. A third possibility is that both happened. Black hole activity and starburst winds working together. The galactic center rarely gives us one clean cause. It prefers overlapping systems. That is what makes the Fermi bubbles so important. They suggest the Milky Way's center has a memory, a record of past violence written in gamma rays. Today, Sagittarius A star looks quiet, but the bubbles hint that quiet may only be the current chapter. At some point, the center may have exhaled, a blast of particles and energy leaving the core, rising out of the disk, expanding into space, and leaving behind a structure so large that light itself needs tens of thousands of years to cross it. Picture a candle that looks almost dead. The flame is small, the room is dark. Then you notice the walls are covered in burn marks. That is the galactic center. Quiet now, but not always. The Fermi bubbles are those burn marks, and they connect back to almost everything else in the region. If the center launched powerful outflows in the past, those outflows could shape the cosmic ray environment. They could help explain why particles move differently near the core. They could interact with the magnetic fields. They could affect the gamma ray glow. They could even be part of the same larger circulation system that turns the central molecular zone into a one-way gate for high-energy particles. This is where the galactic center becomes difficult to separate into chapters. The gamma-ray excess is not floating alone. The Fermi bubbles are not separate decoration. The cosmic ray wall is not an isolated oddity. They may all be different symptoms of the same engine. A black hole that is quiet today. A dense star-forming region that explodes in cycles. a magnetic field system that channels particles, a galaxy center that breathes over million-year timescales. And we are only catching one frozen moment in the breath. That is why scientists are cautious. If you look at one piece alone, the answer can seem simple. A glow might be dark matter. A bubble might be a black hole outburst. A particle barrier might be magnetic shielding. But when all the pieces are placed together, the center becomes less like a puzzle with one missing piece and more like a machine, with several moving parts we have not yet seen directly. The bubbles above and below the galaxy tell us that the center can affect regions far beyond itself. The black hole may be small in visible size, but the consequences of activity near it can reach across enormous distances. And if that is true, then the center of the Milky Way is not just a place where strange things happen. It is a place that sends its consequences outward, into the halo, into the disk, into the future path of gas, stars, and particles. A hidden engine with visible scars. The discovery did not look like the clean, dramatic reveal of a planet or a black hole image. It appeared in survey data, a source that was there, then not there, then there again. To most people, that sounds simple. Things in space brighten and fade all the time. Stars flare, supernovae explode, pulsars pulse, black holes feed. But radio astronomers are used to those patterns. They know what ordinary variable sources look like. This one did not fit neatly. That phrase, radio transient, sounds harmless, almost boring. But it describes one of the most important frontiers in modern astronomy. A transient is something that does not stay constant. It appears, it fades, it returns. Sometimes once, sometimes many times. Sometimes with a rhythm, sometimes with no rhythm anyone can find. For most of the 20th century, the sky was treated almost like a still photograph. Astronomers pointed telescopes, collected light, built catalogues, and compared objects. But the universe is not a still photograph. It is a moving signal. Modern surveys are finally watching the sky with enough sensitivity and repetition to catch things that previous generations missed. And when you watch the sky long enough, it starts to flicker. Some flickers make sense. A star erupts. A neutron star pulses. A black hole eats. But some flickers arrive without a clean label. That is what makes the galactic center radio transient interesting. Its polarization suggests strong magnetic structure. Its location points toward one of the most crowded and extreme regions of the galaxy. Its timing refuses to behave like a simple clock. And the absence of a clear counterpart in other wavelengths makes it harder to classify. If a source appears in radio, astronomers often look for it in X-rays, infrared, optical light, or gamma rays. A magnetar might have X-ray activity, a flare star might show optical changes, an accreting object might show emission across multiple bands. But when an object speaks mostly in radio and only sometimes, the list of explanations narrows in strange ways. It may be a neutron star in an unusual state. It may be a magnetized compact object interacting with nearby plasma. It may be a member of a class we have only begun to define. Or it may be something familiar wearing an unfamiliar mask because the galactic center environment changes how signals travel. That last possibility matters. A signal born near the galactic center does not travel through empty nothing. It passes through plasma, through magnetic fields, through turbulent gas, through the same messy environment that blocks light, scatters particles, and distorts our measurements. By the time the signal reaches Earth, it carries the fingerprints of everything it crossed. This is why one strange radio source can teach us about more than itself. It becomes a flashlight shining through fog. The shape of the beam tells us about the fog. Extension 3. Central molecular zone expansion. To understand why these signals become so distorted, you have to imagine what the central molecular zone is actually like. It is not a clean ring of gas. It is not a smooth disk. It is a crowded, pressurized, turbulent environment where almost everything is moving, heating, colliding, and being pulled in different directions. If our local neighborhood of the Milky Way is like a calm suburb, the central molecular zone is the industrial center of the galaxy. Dense, noisy, hot, full of motion. Clouds there are not quiet round shapes floating peacefully in the dark. They are stretched into streams, compressed into ridges, shocked by collisions, threaded by magnetic fields, pushed by stellar winds, stirred by gravity. Some regions contain enough raw material to build huge numbers of stars, yet refuse to collapse the way simpler models say they should. That is one of the great contradictions of the galactic center. The ingredients are there, the density is there, but star formation is strangely inefficient. It is like walking into a kitchen filled with flour, water, heat, and tools, but finding almost no bread. Something is interrupting the recipe. Turbulence may be one reason. If gas clouds are constantly stirred, they cannot settle easily. They may be dense, but motion inside them acts like support, holding them up against gravity. Magnetic fields may add another kind of support. Charged particles and ionized gas do not move freely across magnetic field lines. They can become guided, trapped, or resisted by invisible structure. Tidal forces from the galactic center may also stretch clouds before they can collapse. A cloud that might form stars in a quieter part of the galaxy can be pulled and sheared in the central region until its collapse is delayed or prevented. And then there is feedback. Massive stars that do form do not live quietly. They blast radiation. They drive winds. They explode as supernovae. Each new generation of stars can disrupt the next. The central molecular zone is therefore both fertile and hostile, full of fuel, full of interference. A place where the galaxy seems ready to build stars but keeps disturbing its own construction site. That matters because this gas reservoir may be the key to the black hole's future. Sagittarius. A star is quiet today because very little material is falling all the way in. But the fuel is not absent. It exists nearby, locked in clouds, streams, and turbulent structures. If some of that gas loses energy and moves inward, the black hole can brighten. Not instantly, not like flipping a switch, but over cosmic time, the feeding rate can change. A quiet black hole can become less quiet. A dim center can flare. A galaxy that looks calm can reveal the burn marks of a previous outburst. This is why scientists care about the central molecular zones so much. It is not just scenery around Sagittarius A star, it is the pantry, the fuel reservoir, the weather system, the chemical laboratory, and possibly the reason the Milky Way's center changes between quiet and active phases. And the chemistry itself is stranger than most people expect. Dense molecular clouds are not just collections of hydrogen. They contain carbon monoxide, ammonia, methanol, formaldehyde, and many other molecules astronomers identify through their radio signatures. Some of those molecules are fragile. Some are complex. Some form only under particular temperatures, densities, and radiation conditions. In calmer regions of the galaxy, molecular clouds can be cold and dark, slowly collapsing into stars. In the central molecular zone, the gas is warmer, more turbulent, and more chemically active. Shocks can drive reactions. Cosmic rays can ionize gas. Magnetic fields can shape flows. Radiation can destroy molecules in one place while dense gas shields them in another. The result is not one uniform chemistry. It is a patchwork.